All right, let's get started again. Thank you all for coming back. Our next speaker in this new session, session 2, is Professor Stephen Lowe. He's Gilun Professor of Computation and Mathematical Sciences and Electrical Engineering.
Thank you very much. Thank you very much for coming. Not too loud, right? Okay. And thank you, Azita, for organizing the workshop and the nice opportunity to talk about the decarbonized energy system. So I'll start with the motivation and then tell you 3 examples of some of the things that we do in my lab. So temperature rise can cause all kinds of crises, humanitarian, economic, refugee, which can cause political and even national security crisis. And that's due to greenhouse gas emissions, which is really driven by the global economy that is enabled by energy use. And if we look into energy use, we will see electricity generation and transportation accounts for most of the emissions. And therefore, if we want to drastically reduce emissions, we have to electrify everything almost and generate electricity from clean renewable sources. So electric vehicle is one part, an important part of the smart grid revolution that is ongoing now. So this is a familiar story, but it is still astonishing to look at the underlying numbers. It's astonishing because scientists told us half a century ago, warned us about this crisis, yet 50 years on, we are still debating how or if we combat this crisis. So let's look at some of the numbers. So this is the correlation between CO2, atmospheric CO2 and the temperature over the last 800,000 years. So one thing we note is that there's a very strong correlation between the 2 trends. Both are cyclical with about 100,000 years cycle. And this curves, both curves, is up to about 200 years ago. So we'll come back to this curve and look at what happened in the last couple hundred years. And this, again, is over 800,000 years. So because it's not only a correlation, we understand the mechanism through which emissions lead to temperature rise. And therefore, it's reasonable to believe it's not only a correlation, but actually a causal relationship between the 2. So if we look at, for the last couple hundred years, how the temperature has been changing. So this is global average temperature. And the main conclusion is that after Industrial Revolution, the global average temperature has increased by more than 1 degree Celsius. If you look at the local temperature, not the average over the entire globe, then some parts of the globe can have an increase up to 9 degrees Celsius above the baseline. And the baseline in this case is the average temperature over 30 years from 1961. Okay? And therefore, we see that for the last, say, couple hundred years, the temperature has been rising quite rapidly, and we would expect the atmospheric CO2 will also rise. And indeed, that's what we see. If you look at, say, the last 10,000 years, the atmospheric CO2 has been relatively stable around 240 or so until about a couple hundred years ago, and it shot up. If we look at the last 800,000 years, which was the picture that we saw before, not only the rate at which the atmospheric CO2 has been rising so much faster for the last couple hundred years, the height is also much higher. So over the last 800,000 years, the peak is less than 300 parts per million. We are now at 420 parts per million. So if we look at CO2 emission, say from 1750 by country, so there's the EU, or Europe, including EU, US, China has been rapidly increasing since the 80s, and Asia. If you look at the cumulative CO2 emission, US still the highest, EU is the second, but China is rapidly catching up. So these are the pathway to limit the temperature rise, hopefully below 2 degrees Celsius. Is possible if we act. I guess the optimistic note is that not too long ago, we were talking about 4 degrees Celsius. Now we're talking about 1 to 2 degrees. So that's the hopeful sign. If we look at the net zero greenhouse gas pledges around the world, different countries or different states in the US and so on, there are all many different types of net zero pledges. Some of them are pledges, some of them in policies, some have been enacted in law, some have been achieved. All this combined, today it covers 83% of the emissions, 91% of GDP, 80% of the population. So there's hope compared with, let's say, 2019. So this is the 2022 numbers, and 3 years earlier, the coverage is only 16% of GDP as opposed to 91%. And so 2 questions. Why are we emitting so much? And how do we emit so much? So the first question, if you look at the emission per capita, so this is consumption-based emission per capita, versus the GDP per capita, you see this very strong correlation. So US, China, all these different countries. So this is 2020. How has GDP per capita evolved over time? So that's the picture. So this is the GDP over the last 2,000 years. So we see that the standard of living shot up over the last 100 years or so. And the x-axis, unlike the other plots we have seen so far, the x-axis is not time. It's how wealthy a country is. And it clearly shows the energy inequity. So the US consumes about 15.5 tons versus its neighbor, 3.4. Australia, Indonesia, neighbor, Switzerland, and Portugal. So then the second question, how do we generate so much emissions? In the US, say 2021, 82% of greenhouse gas emission is due to energy use. At Caltech, it's 92%. And electricity generation and transportation, they consume 65% for all primary energies. So all primary energies are coal, natural gas, petroleum, geothermal, bio, wind, solar, hydro, all kinds of primary energies. These 2 activities consume 65% and emit more than half. And therefore, to drastically reduce greenhouse gases, we have to electrify transportation and generate electricity from renewable sources. So these are the 2 types of activities we have been working on in my lab. And let me tell you a couple examples. And so this is 2021. We only improved by 2% from 2019. So the rate at which we need to reduce, unfortunately, needs to be a lot higher. So EV charging. So the situation in California is that we have a commitment to have 60% renewables by 2030 for power. When it was first proposed, it was 50%, but now it looks like we will exceed the target, so it has been upgraded to 60%, and 100% clean electricity by 2045. On the transportation side, the goal is to have 1.5 million zero-emission vehicles, think of them as EVs, even though hydrogen cars also counts, by 2025, and 5 million by 2030. When we have large-scale deployment of electric vehicles, we will not only have a cleaner air, it also is an important mechanism to help integrate renewables that we need to deploy in order to have 100% clean electricity. So for example, for those who might heard of this, this is what's called a duck curve in California. So this is 24 hours, and this is the net consumption, that is the total consumption minus the solar. So this will be the net consumption that needs to be met by, for example, fossil generations. So we see a dip, and this creates a lot of problems for the grid because of this sharp rise. So the current system cannot handle the sharp rise. But if we have workplace EV charging, we can fill the value of this gap by charging EVs at workplaces. Right? So the cars mostly either at home or at workplaces. And if we want to fill the valley, so this is the valley of 2021, we can already charge 30 million EVs. California has about 50 million or so vehicles. So there's a huge potential not only to clean the air, but also help manage the grid. So there's also some surveys that drivers are twice as likely to get EV when workplace EV charging is available. So let me tell you one project that we finished recently. So before 2010, my lab works entirely on internet congestion controls and so on. Around 2010, so we completely switched to look at energy systems. And one thing that is important that we learn is that it is very important to maintain a broad-based theory research. Not all good research, especially not all good theory research, is or needs to be useful. Sometimes some of them will become useful. So we did a bunch of more theoretical research. 2016, some of those research becomes useful, in particular for EV charging, for large-scale EV charging. So we started to build the infrastructure at Caltech, and eventually we commercialized the technology. So what an interesting thing that we show is that when we started to build this EV charging facility at Caltech, compared with the industry standard at the time, some kind of efficiency measure that the standard industry practice will gain about 28% efficiency. The system that we build can get to 53%. And you can actually prove that under certain consumptions, that's close to the maximum you can get. So around 2016, my former student, George Lee, is a really amazing student, and led a team of students and engineers and so on, built the first large-scale EV charging at Caltech. That was 2016 at California Garage. So this is completely new compared with the industry standard. So this is George and his brother debugging, and so on. And eventually, we commercialized the technology, which was then acquired by EDF, and these are some of the deployments that was done. Okay, so this is the physical system. It includes 2 transformers, or the circuit panels and conduits and wires, and then the most important thing is George put together a smart EV charging from a very low-cost dumb charger. So he created a chip that allows the dumb chargers to do real-time sensing, communication, and control. So S2I, basically. And once he created this thing, we can build this infrastructure and actually implement in software large-scale EV charging through scheduling. Right? Once you have the intelligence, then you can close the loop and control it in a way that is much, much cheaper than otherwise. And this is the cyber or sensing infrastructure. So when an EV is plugged in, the industry standard is that you will start charging at the peak rate. If you're doing EV charging at workplace, that is not necessary, and that is also extremely expensive if you can do smart charging using the sensing and intelligence. So in our system, when an EV is plugged in, you will use the mobile app to tell the system, I need 30 miles or 100 miles, and I expect to leave at 5 p.m., for example. So the system will send the information to the cloud, and every minute, the cloud will solve an optimization problem and figure out the optimal charging rate for every EV in the garage. If you just repeat the cycle, that allows you to charge to a much larger charging capacity for infrastructure at a much lower cost. Okay, so eventually we started a company which was acquired, and the value, so it provides two value propositions. One is to reduce the capital cost. If you want to, say for example, in LAX now, there are about 1,200 EV chargers. Now, if you look at around, this is around 2017 or so, there were California Energy Commission and also the utility companies, they have incentive programs to encourage businesses to install EV chargers. The incentive will pay the businesses about $15,000 per charger. So that's the value they think you would take to, or the cost to install, the capital cost to install per EV charger. With the technology that we developed, George got it down to 3,000. The second value is you will lower the operating cost through 4 different methods. One is that there's what's called a demand charge, which is that for businesses, not for the households, but for businesses, electricity bills actually contains 2 components. One is how much energy that you use. One is the peak load. What is the peak load? And that's called demand charge. At Caltech, for example, 2/3 of our electricity bill is due to demand charge. And therefore, if you can reduce the peak, you can save a lot. By smart scheduling, you can do that. You can still satisfy the energy requirement for every EV before their deadline, but at a way that has a much lower peak cost. The second component is the energy, how much energy you use. And the price for energy may vary over time, over the course of the day. And you can do your smart charging to minimize the overall cost, for example. And the third is that when you charge EVs, you actually earn carbon credits, which has a certain value on the secondary market. And therefore, you can charge in a way, and those prices vary. You can charge in a way that will optimize your carbon credit. And then the third is that you can use it to help the grid, to help stabilize the grid. So when the grid is under stress, you can send a signal to say, slow down or reduce your demand. And indeed, this demonstrates that you can reduce the EV charging demand to help the grid. Okay, we also, once we have the infrastructure, physical infrastructure, we also build a software system that provide open source software system that provide real and high resolution data for the research community. Okay, let me skip that. How much time do I have? 5 minutes, okay. Let me tell you, maybe I'll tell you this, but I will skip the last part. So this is the picture that we saw before in the US. 82% of greenhouse gases is due to energy use. At Caltech, it's 92%. So this is actually an opportunity for decarbonization. So the question, or the problem that we want to address is that we want to do this 24/7 carbon neutrality. And that can be very expensive. So what does that mean? It means that on an hourly basis, we want to consume no more than available renewable, say, wind and solar generations on the grid, for example. In order to do that, you require balancing these volatile renewables with consumption at all times. And that is very difficult unless you have a huge amount of storage, which is very expensive. And as volatility increases, as we have more and more wind and solar on the grid, this becomes more difficult. And the estimate that the curtailment of renewable alone is estimated at 2.7 billion by 2032. So the idea is we want to develop technologies that will drastically reduce both the capital and the operating costs for achieving 24/7 carbon neutrality. And so you require a lot of stuff. You require a whole bunch of infrastructure, so this is not something we can do, but hopefully Caltech will commit itself to do that. Putting the required infrastructure is probably more than $100 million investment. What we can do, though, is we can develop the theories and the algorithm and maybe prototype some of those algorithms that when we have such a system, electrified system, then we can indeed achieve 24/7 carbon neutrality at a much lower cost, right? If you look at, for example, if you look at the Caltech system, the energy system that generates a lot of emissions, it has 3 systems: electric, heating, cooling. Now they operate independently. If you think about the EV charging use case, and sort of translate that to the entire Caltech energy system, it's the same thing. There should be a lot of untapped value if we can jointly optimize the operation of these 3 systems. Right? So that is a technology that we'd like to develop for that. Okay, so the first challenge we have to overcome for this is that the energy data, even though we have access to all Caltech energy data, is actually not very useful at all. It has all kinds of problems just with most real data. And therefore, we end up have to bite the bullet and deploy our own meters so that we get comprehensive, real-time, and reliable data. And we now have such a test bed on campus. So let me say a couple words on the DR test bed. So this is so Caltech has 4 substations. Caltech has a pretty large electricity network. So the peak demand at Caltech is almost 50% of that at Stanford. So we are pretty energy inefficient, maybe. So we instrumented the entire one of the 4 substations. So all the buildings, including this building, we have our own meters, so we get real-time, reliable data. So these are some of the things that we built. Let me skip that. And even though the project just started, so we just started and are still working on that at the initial stage, it already has interesting benefit. So in mid-September, there was an outage that affected the several substation buildings. And Caltech facility, unfortunately, didn't know about this until 2.5 hours later, when an angry professor called. So the system that we built allows us to we'll be able to do real-time detection and alert, and also reconstruct second by second the entire event. So we see exactly what happened, and then how the system responded. It has problem, it closed again, all kinds of stuff. Okay, so we're working with Caltech facility and try to create a tool that they can use. The second thing that can be done that we haven't finished doing that is if we want to really do accurate real-time carbon footprint calculation, then you need the kind of system that we're building in order to do that. And this may be required in the future to report accurately Scope 1 and 2 greenhouse gas emissions. So the last example that we give is that, so for electrical engineers, we may recognize this. The current is a vector. Current vector is related to voltages. So you have a network, nodes connected by links, and at each node there's a current injection, there's a voltage. Right? So these are phasors, complex numbers. And the vector of currents current injections are related to the voltage vector at the nodes by this matrix, what's called an admittance matrix. Okay? It's complex symmetric matrix, that's why it's difficult. Okay, so this Y matrix describes the network. It's a network model. It tells us the topology, it tells us the line admittances. And this model is very important. This Y matrix is very important because numerous control optimization schemes assume Y is known. Now, for distribution systems, typically they are not known. So at Caltech, we don't know. The local utility, PWP, they don't know, right? And therefore, the question is that can you have measurements of, say, voltages and currents, and then from that, you can learn the network, right? Sense to S2I. It turns out little is known about the properties, analytical properties of Y. And state of the art is to say, if we measure the voltage and current at every node in the network, then there are different algorithms you can use to estimate Y. But in reality, you will not be able to measure at every node. If you have hidden nodes where you don't have measurement, can you still do it? Well, if you only have, let's say in this example, so these solid dots nodes are the ones where you have measurement. So these are the measure nodes. The unshaded nodes are hidden nodes where you don't have measurement. Then what happens is that if you look at the set of measurements of voltages and currents, they will be related linearly by, so this is the vector of currents at the measure nodes, vector of voltages at the measure nodes. They will be related linearly by another matrix Y bar, which is what's called the third complement of the original matrix, which is what we're interested in. Now, from the measurement, I can estimate Y bar, that's fine. The question is, can you identify the original matrix Y from the estimated Y bar? Now, pictorially, this is the network we have. This is the Y that describes this network. But what we can see from the measurement is a mesh network, fully connected network among these measure nodes. And the corresponding Y bar describes sort of the virtual network on how these measure nodes are connected. It's not very clear that you can go backward. In fact, in general, you cannot. So mathematically, given a Y matrix, it's complex dimension matrix, you can do the third complement, which gives you the Y bar that describes the virtual network. The question mathematically is, when will the inverse exist? Well, it turns out that inverse will exist if the network is a tree. Who care about the tree? Almost all distribution systems, that is local power distribution systems, have tree topology, except for, say, San Francisco, Long Beach. Almost all other distribution systems have the tree network. So I think I'm done. Yes, thank you very much.
It's really exciting to see Caltech working on energy and sustainability. One of the issues that we have as we electrify is immunity and resilience. How do you factor that in mathematical equations that typically don't take that into account?
Yeah, very difficult question. So let me give you a very brief answer, but if you're interested, we can discuss in detail offline. It is very difficult. So two difficulties. One is that how do you capture mathematically some of those resilience issues? And there are many issues within the umbrella of resilience. Some of them you can capture mathematically. Then you say, once you capture mathematically, can you solve that problem? Can you solve the mathematical problem in order to optimize or minimize your costs or emissions and so on? So that's difficult, but probably doable. The harder part is there are notions that's not very clear how you can capture mathematically. And not very clear, except some ad hoc. Maybe AI can help. Maybe you have hope. So AI is most helpful, at least one instance where it is most helpful, is there's no good model, right? So the stuff that I've been talking about, they are good models. It's just that the models we may not know accurately, and then you can try to use measurement sensing to try to get to a good model and then allow you to do good control. Okay, thank you very much.
Thank you so much.